Okay, class, now we are going to discuss this assignment 10E for halogenal alkanes. Okay, so let's first take a look at the question. Question 1. What is the type of mechanism and the important feature of the reaction between this halogenal alkane and aqueous NaOH? So for the chapter for halogenal alkane, the first thing is that we have to try to classify the type of halogenal alkane. So after you classify the type of halogenal alkane, then you can choose the correct mechanism. So if we sketch out this drawing, this structure, it will look something like this. So you can see that it's a tertiary halogenal alkane, which has 3R groups over here. So given a tertiary halogenal alkane, you will find that if you recall, it undergo the SN1 reaction. Okay, and if you remember, SN1 reaction is made up of 2 steps, and the first step involves the formation of a carbocation. So the answer will be an SN1 mechanism. Now it's between a transition state or an intermediate. So the difference between an intermediate and a transition state is over here. So if we sketch out the energy profile diagram, right? Now, at this point here, where the substance will have very high energy, this is known as the transition state. And over here, this point over here, which is the starting reactant of the second step, and is something that is formed during the first step, so we call it intermediate. So in the SN1 mechanism, it involves 2 steps. The first step forms the carbocation intermediate, and then the second step, the carbocation intermediate, undergoes a further reaction to form the substituted product. So therefore, the feature of an SN1 reaction will be an intermediate. Next, let's go to question 2. Which statement about substitution reactions are correct? So let's look at the option. So the reaction between aqueous NaOH and 1-chloropentane predominantly follows an SN2 mechanism. So before we can answer that, first again, classify it and check whether it's a primary, tertiary, or secondary halogenal alkane. So 1-chloro, if you look at the structure, is something like this. So you can see that it's a primary halogenal alkane. So being a primary halogenal alkane, it tends to follow the SN2 mechanism. So this is correct. The reaction between sodium hydroxide and 2-chloro-2-methabutane predominantly follows SN2. So sketch the butane. Number 2, there's a methyl group, and then there's a chloro group. So if you just briefly sketch the structure, you can see that this is a tertiary halogenal alkane, which has 3R group 1, 2, 3. So therefore, it can't be following the SN2 mechanism, but rather the SN1. So this is not correct. All right. Now the next question, so only one is correct, and the last one, if you look at the options, the reaction of sodium hydroxide with 1-chloropentane occurs at a slower rate than 1-bromopentane. So you can see it's a 1-chloro versus 1-bromo. So over here, what we are looking at is more on the halogen CX bond strength. So we have a CCl versus a CBr. So in a nucleophilic substitution, we need this bond to break. So whichever has a weaker bond energy will mean that the activation energy for the reaction may be lower, and therefore a faster rate of reaction. So since CCl has a greater bond energy, so you can find that the activation energy will therefore likely to be higher, and therefore the rate of reaction will likely to be slower. So it will be 1 and 3. The answer will be B. Now, which halogenal alkane will react most quickly with sodium hydroxide? So this is testing you a different type of concept. Firstly, there are factors which affect the rates of halogenal nucleophilic substitution. So there are 4 factors. First factor will be whether it's an SN1 or SN2. Second factor will be the type of nucleophile. Third factor will be the type of halogen. And the fourth factor will be the type of solvent. So these are the 4 factors that affects the rate of a reaction of a nucleophilic substitution. So if you look at this question here, the nucleophile is the same. So we don't have to consider the type of nucleophile. And they didn't mention the solvent, so we can remove the effect of solvent. And if we look at the options, we do see some primary, tertiary, and tertiary. So we have this SN1 or SN2. So if you remember, SN1 reactions tend to happen faster than SN2. So therefore, it will not be A, it will not be B, because C and D proceeds via the SN1 mechanism. So the second factor we have to consider is the CX bond strength. Okay, as seen earlier, the CCl bond strength is actually much stronger, and that presents a greater activation energy for the reaction. So therefore, CBr will definitely react with a faster rate. Question 4. The organic compounds P and Q are formed in a 2-step reaction. So the first step reaction, we have a nucleophilic substitution. How do you know? You look at this. This is a halogenal alkane, and this is an aqueous NaOH, right? So it will be a nucleophilic substitution where the position of the halogen will be substituted by the nucleophile, which is OH. And then over here, this substance undergo an oxidation reaction. And how do you know it's oxidation? You look at this. This is a dichromate. Dichromate is an oxidizing agent. So in order to predict the product of an oxidation reaction, we need to classify the alcohol. So if you sketch this alcohol, you'll find that you actually end up with a primary alcohol, where you have 2 H's and 1 R group. So a primary alcohol under a reflux condition where you are refluxing will therefore give you carboxylic acid. So therefore, if you choose the answer, you should get B, where you get an alcohol and a carboxylic acid. Now, I know both of them gives you the carboxylic acid, but if you count the total number of carbon, you should only have 4 carbon. So therefore, the option 1 is wrong. You have 1 plus 3 plus 1. So you have 5 carbon here. Question 5. What are the correct names of the type of reaction? So you can, if you recognize the functional group, will be easier. This belongs to the functional group of an alkane. This obviously is a halogenal alkane, and this will be an alcohol. Now for alkanes, they don't have many reactions. So basically free radical substitution, right? And then if you look at the next step, what are we doing is that we are replacing the Cl with an OH. So replacing a Cl with an OH is a form of substitution reaction, and therefore the answer is D for dog. Okay, now we will look at the structures. Okay, the structure questions are really very long. Okay, so bear with me. There are several structures with a molecular formula of C5H11Br. Deduce the name of one of the isomers which can exist as enantiomers. So in order for something to exist as enantiomers, we need a chiral carbon. That means it has 4 different substituents. And there must be no plane of symmetry. Right. So yeah, after you identify that, you're supposed to draw a 3-dimensional structure to show the two enantiomers, because enantiomers can only be represented by three-dimensional structures. So how do we work it out? First, you count how many carbon you have. So there are 5 carbon, so 1 must be the center. Now, then you must have different substituent, right? So for example, you may want to use a Br, and then one of the group be a H, right? So we still have 4 carbon, so you can't distribute 2 and 2, because if you distribute 2 and 2, then you will have 2 similar groups. So you may have to distribute, let's say 1 CH3, 1 and 3. So you have a CH2, CH2, CH3, right? Now, obviously, but this structure is not a 3-dimensional structure, but it's just to show you how to achieve that chiral carbon. Now we convert it into a 3-dimensional structure. So we will have one of them which is out of plane, and then another will be behind the plane, right? So with this, now what you do is that you will prepare its mirror image. So what you can do is that you can just visualize a mirror. Now you copy this whole thing over. See, the group that is closest to the mirror is the CH3. You can see this group here is the closest to the mirror. So you do the same for that. Sorry. So you will put the CH3 here. All right, and then you have the H, and then you have the Br, and then this group, just copy back. This will be its enantiomers. Okay, there's more than one answer for this question. So this is one possible structure. Is called 2-bromopentane. Okay, there are other possible answers. I'm going to show you the other possible answers now. So the other possible answers will be 1-bromo-2-metylbutane, which looks like this. Okay, maybe I should draw the straight chain one so you can see. So 1-bromo-2-methyl. So at number 1, we have a bromo and H. Number 2, we have a methyl. Something like this. So you can see this carbon here is a chiral carbon, because this carbon here has actually 4 different groups, a CH3 group, an ethyl group, a H, and a CH2Br group. So you can do the same and draw it in the 3D format. Okay, another structure that is a possible answer is a 2-bromo-3-metylbutane. Okay, so let me sketch it out. 2-bromo, number 2, there's a bromo. Number 3, there's a methyl. Okay, so you have something like this. So if you look at the structure, again, you have 4 substituents, 1 bromine, 1 CH3, 1 H, and 1 other group. So this is again the chiral carbon. Okay, so any of the structure presented, you are supposed to deduce the name. So if you are drawing the one that is above in this diagram over here, the name will be known as 2-bromo, 2-bromo. Oh, sorry. It will be 1-bromo, 2-methyl. If you are drawing this, if you are drawing the one below, then its name will be 2-bromo, 2-bromo, 3-methyl. Okay. Okay, can I use space to write? Okay, something like that. All right. Okay, let's move on. Okay, so now we are at 6B. All the isomers react when warm with dilute aqueous solution of sodium hydroxide. The reaction of 1-bromopentane proceeds by SN2 mechanism. Describe this mechanism using structural formulas and curly arrows to represent the movement of electrons. Now, mechanism question, I have to look at your answer. So can you try these two questions and then I will check the answer on Wednesday, because you cannot see your own mistake in the mechanism. So for these two questions, can you spend this time to draw it now? But I will go around to check your drawing on Wednesday or Thursday when we go back to school. But I need to see the mechanism. Okay, so I will not show you these two first because I need to see your own drawing. Okay, so we'll proceed on to B part 3. Explain why 1-bromopentane proceeds by SN2 mechanism while 2-bromomethylbutane proceeds by SN1. So if you recall, SN1 mechanism involves the formation of a carbocation, right? And a 1-bromopentane is actually a primary halogenol alkane. And a 2-bromo-2-methylbutane is actually a tertiary halogenol alkane. So it makes a difference in terms of the stability of a carbocation, right? So, but how are we going to present and explain very clearly the carbocation? So we can state that no, 2-bromo 2-methylbutane forms a tertiary carbocation, while 1-bromo, I think you need to state the type, it will be easier. While 1-bromopentane forms a primary carbocation. Okay, intermediate. So if you actually you should spell carbocation. So let's do it once. Okay, so carbocation. So you need to talk about the stability. So the tertiary carbocation is more stable than the primary carbocation. Right, so therefore the primary carbocation will not usually be formed. So it forms a tertiary carbocation which is more stable. And how is it stabilized? It's stabilized by the positive inductive effect of the electron donating alkyl group. Okay, let me explain this. So if you use 1-bromopentane and if you allow it to proceed by SN1 mechanism, you will end up getting this. This is the carbocation. So you can see that this is our primary carbocation, which has only one R group. So this is the primary carbocation, right? Whereas if you use a 2-bromo-2-methylbutane, you'll get a carbocation which is like this, which is a tertiary carbocation. So you can see that the difference in a primary carbocation, there's only one alkyl group. While in the tertiary carbocation, you have 3 alkyl group, right? And this alkyl group are actually electron donating group. And because of their nature, they are electron donating group, they can actually donate electrons via this inductive effect to the carbocation in the center. So therefore, it helps to reduce the charge, positive charge on the carbocation and stabilizing it. All right, so that is if you answer based on using SN1. But of course, we also have to explain why a tertiary carbocation cannot proceed by SN2. So there's a second part to the answer. So if we use a tertiary carbocation, if we look at it, if we look at a tertiary halogenol alkane. All right, so let's put back the halogenol alkane now. Okay, so if we have a tertiary halogenol alkane where the group is, this is a primary and this is a tertiary. So you can see that a tertiary halogenol alkane has some bulky groups around it. 1, 2, 3. Now, the nucleophile needs to attack from the opposite side of the bromine. So therefore, the bulky alkyl groups in the tertiary halogenoalkane will present steric hindrance to the nucleophile. And prevents it from approaching prevents it from approaching the carbon atom. Now, which carbon atom are we talking about? We are talking about this carbon atom here, this one, right? So you see all these big groups are going to block the nucleophile from accessing this carbon. Whereas in a primary halogenoalkane, the hydrogen atom is a very small group. So all these are very small groups. So which means that the nucleophile will be able to access this more easily compared to in a tertiary case. So in an SN2 mechanism, the nucleophile needs to approach the carbon, which is bonded to the halogen. So the bulky alkyl groups in a tertiary halogenoalkane will present steric hindrance and prevent it from accessing it. All right, that is for question. This question here. Next, we're going to go on to the next one. Why hydroxide is a better nucleophile? So if we look at hydroxide it has charge of OH minus, while water is basically neutral, right? So we can see that it has a negative charge. And not only that, because it has a negative charge, you have a greater electron density. So you have a greater electron density and it makes it a better nucleophile. All right, okay, now with that, next, let's look at the boiling point. Explain whether the boiling point of 1-bromopentane will be higher or lower than that of 2-bromo-2-methyl-butane. So if you look at it, they actually have the same MR. So 1-bromopentane, I have 5 carbons arranged in a straight manner, linear manner. Okay, while a 2-bromo-2-methyl-butane also consists of 5 carbon, but now it's arranging in a branch manner. Right? So what we are looking at here, the concept here is about branching. Which concept? Branching reduces the surface area. So when branching reduces the surface area, the effect on the intermolecular force will be weakening the London dispersion force, right? So over here, we are talking about the weakening of the London dispersion force due to increased branching, reducing surface area. All right, so that's the idea here. So in your answer, you must talk about branching, surface area reduced, weaken LDF. With that, let's move on to the next question. Question 7. Okay, we still have 2 more questions for this. Now, below are 4 structural isomers with the molecular formula. So which one will react exclusively by using sodium hydroxide via SN1? So our job here first is to classify again. So you can see this one has the white color balls represent hydrogen. So therefore, this is a primary halogenoalkane. Now this over here, it has 2 alkyl group. So it's a secondary halogenoalkane. And over here, it has 3 alkyl groups. 1, 2, 3. So it's a tertiary halogenoalkane. And the last one over here, look carefully, these are hydrogen. Okay, so we are only looking at the carbon. We are only looking at this carbon because this carbon is the one that contains the bromine. So we find that if we look at this carbon, it has 1 big alkyl group and 2 other hydrogens. So only 1 alkyl group, so primary. So in order for something to react exclusively by SN1 mechanism, we are looking at the tertiary halogenoalkane, and therefore is the isomer C. All right. Okay, so we have to name it. So identify and name it, right? So how do we call this isomer C? So if the longest chain consists of 3 carbon, so it's called a propane. And then on the propane, there's a methyl group, so it's called 2-bromo. And there's also a bromine group. So 2-bromo, 2-methyl propane. Okay, something like that. Okay, next question over here. You are supposed to use the formula to represent bromoalkane and write an equation for the rate determining step. So we are only focusing on the first step, which is the rate determining step. And that step involves forming carbocation. So our equation will be RBr arrow. Okay, we are using RBr to represent the bromoalkane. R plus Br minus. This is our carbocation over here. All right. Now, next, identify one isomer that will react with NaOH exclusively by SN2. So only by SN2, so we are looking for a primary halogenal alkane. Right? So we are going to look at the primary halogenal alkane, and the answer could be either A or D. So you can use A or D as the compound to draw. So how do we name A? A will be called 1-bromobutane, because you can see that there are 4 carbon in a row and a bromine on the first carbon. Now this over here, we need to choose the longest chain that has the bromine here, so that it's easier for us to name. So it will be called 1-bromo, 2-methyl propane. Sorry, there's no dash here. 1-bromo, 2-methyl propane. Right. Now we are supposed to draw the mechanism. Again, I want to check the mechanism tomorrow when I come back to school. Sorry, I want to check the mechanism on Wednesday when we come back to school. Okay, because the problem in mechanism is that you can never see your own mistake. So you need somebody to check for you. Okay, and then next, we are supposed in your mechanism, we are supposed to include the structure of the transition state and the organic product and the curly arrows. Okay, so again, we will I'll come back to school to check your answer for this. Everybody will show me your answer. Everybody has to show me this to show that you know actually have done your work. So these highlighted questions all have to be shown to me. Okay, state and explain how the rates of part 1 and part 2 are affected when NaOH is doubled. So let's look at part 1. So if you look carefully, part 1 here is about SN. Part 1 here is about SN1. So SN1, the 1 here tells you unimolecular. That means, right, in the rate reaction, there is only the halogenal alkane in the rate equation. Is unimolecular, 1 molecule. This is SN2. With the 2 over here means bimolecular. That means, right, in the rate equation, we will have 1 mole of Rx and 1 mole of OH minus. So it's bimolecular, 2 because of 2 molecules in the rate determining step. So you can look at this and identify how the rates are affected when the sodium hydroxide is doubled. So if you look at the equation, you'll find that the first one, SN1, is 0 order with respect to OH. 0 order, right? So 0 order, therefore, the rate of SN1 will not be affected. So the rate of 1 will not be affected. While the rate of number 2, since you double the amount of hydroxide, the order is a first order reaction. So the rate of reaction 2 will also double. Okay, understand? Okay, done. We are done with this. Now, state and explain how the rate of reaction of 1 bromo versus 1 chloro. Again, bromo will be faster because of a weaker bond energy. So this will be faster as it has a weaker bond energy. All right, it has a weaker CBr bond compared to a CCl bond. Okay, so that is for part C. Next, okay, question 8. Question 8 over here, 1-iodoethane reacts with sodium hydroxide. Explain the mechanism. So again, we need to know whether it's SN1 or SN2, right? So this one over here, if you draw the structure, iodoethane is an SN1 reaction because these are hydrogen. SN2 reaction is a primary halogeno alkane. So, okay, for this one, again, show me your drawing when we come back to school. I need to see the drawing to highlight to you what are the things that to look out for. All right. So I'll not show you the answer. I want you to show me your drawing. State the rate equation for the reaction and the molecularity of the rate determining step. So since this one is a primary halogeno alkane, it's an SN2 reaction, so the molecularity will be 2. And the rate equation will be rate equals to, now we cannot put Rx, must put 1-iodoethane. Okay, now suggest why polar aprotic solvents are more suitable for SN2 reaction, whereas polar protic solvent would favor SN1. Okay, let's try to understand the solvent again. So we have aprotic and we have protic. So aprotic solvent, they are the solvent that cannot form H bond. Protic solvents are the solvent that can form hydrogen bond. So that's the first thing you need to know. Now, an aprotic solvent will actually solvate the cations, but not the anions. A protic solvent will solvate the cations and the anions. So therefore, you'll find that for aprotic solvent, because it will for the aprotic solvent, which is this one, since it solvates the cations, so it will in a way help to stabilize any mechanism that has a cation. And it does not solvate the anion, so therefore it doesn't surround itself around the nucleophile and solvates the nucleophile. Now, solvating the nucleophile makes the nucleophile less reactive, right? So therefore, you will find that the properties here is very suitable for SN. So the property here is very suitable for an SN2 reaction. Okay, why is it suitable for SN2 reaction? Because in an SN2 reaction, we need a very reactive nucleophile, right? And since, right, this aprotic solvent does not solvate the nucleophile, which is the anions, so it will make the in a way the nucleophile will be very reactive there. All right, because we need a reactive nucleophile. So first thing we can see is that it actually does not solvate the nucleophile, and therefore nucleophile is very reactive and speeds up the SN2 reaction. That is the first point. All right. Now, the second point over here is that we need a nucleophile for the SN2 reaction. Now, you'll find that the aprotic solvent, it actually solvates ions. The sodium cation over here. So it solvates the cations, which is the counter ion of the nucleophile. And since it can solvate the counter ion of the nucleophile, therefore, it will actually help to form the nucleophile more readily. So therefore, the reactivity of the nucleophile is very high. Okay, example, okay. So in example, it solvates the Na plus. Remember NaOH. So it solvates the Na plus. And by solvating the Na plus, it helps to separate, dissociate the NaOH into Na plus and OH minus. And then it doesn't solvate the nucleophile, which is the OH minus. So therefore, the OH minus is very reactive, and this helps to speed up the SN2 reaction. The protic solvent, on the other hand, solvates the cations and the anions. So because the protic solvent solvates the anions, means over here, it will actually reduce the reactivity of the nucleophile. So as it reduces the reactivity of nucleophile, so it's not that suitable for SN2 reaction. So therefore, a protic solvent is more suitable for an SN1 reaction. Right? And in an SN1 reaction, if you remember, one of the important feature of an SN1 reaction is the carbocation. So over here, we have something that can solvate the cation, which that it can solvate the carbocation. So this property of being able to solvate the cation will actually help to stabilize the carbocation intermediate. And as it stabilizes the carbocation intermediate, it will actually lower the activation energy for the reaction. So it will speed up SN1. All right. Okay, last question over here. Deduce with reason if water or DMF is a better solvent. So we need to know how to draw DMF. Now the formula is given here. So we can just try our best to draw the DMF. So let's try to follow. So you have a H, you have a C, O. Okay, DMF, if you read the name, from the name you can tell it's an amide. So I have CO and this N has two CH3 group. Okay, so after you have finished drawing the structure, you look at it and you see whether it can form intermolecular hydrogen bond. So you don't see H bonded to OFN here, right? So therefore, it has no hydrogen bond formation. So therefore, it's an aprotic solvent. And aprotic solvent tend to stabilize or more suitable for SN2. So therefore, this aprotic solvent is more suitable for SN2, right? So if we look at this, then they ask for deduce if this is a better solvent. So if we look at in context with this question at the top part of this question, we are looking at the SN2 mechanism, right? So then if we refer back to this, if water or DMF is a better solvent, then it definitely will be DMF, because DMF is an aprotic solvent and it will actually speed up SN2 mechanism. So DMF will therefore fits this this reaction better, since we are looking at the SN2 mechanism. So now we have done with this. Okay, so we will stop here.